everyone, and welcome to my lab. Are you ready to have some fun? Yeah! Are you ready to learn? Yeah! Well, let's get started then. Here we go. And I want you to pay special attention to what's going to happen, because I promise you a good time, especially if you pay attention. So be on the lookout for smoke, flames, explosions, color changes, and be as attentive as possible. I want you to make observations and to try to connect these observations to experiences you already have had. When we do scientific experiment, we always obey the safety rules. And I would like everyone to notice that I have my goggles on, because it is the state law that we must have eye protection. I also would like you to notice that we have a fire extinguisher right here, ready to be used just in case something goes out of control. We're not planning on anything going out of control, but we have it as a safety precaution. And I want you to be paying special attention to all kinds of changes that might happen. Be on the lookout for color changes. Be on the lookout for smoke, fires, explosions, and try to think about what you see and what you hear, and try to connect it with experiences that you've had in the past. Now you notice that we have some balloons up in the air. How many are there? 6. And what color are they? And what do you suppose we have in those balloons? Some of you are saying helium, because you know from experience that helium-filled balloons are lighter than air. I'm going to tell you now that helium is a gas that does not burn. So one way to find out what's in those balloons is to take this flame from this torch and try to ignite what's in the balloon. I notice some of you are covering your ears. Why are you covering your ears? Because you know from experience that there might be some sound energy accompanying what might happen. With our eyes, we see light energy. We have a combustion reaction taking place right here. It's a controlled combustion reaction. It releases energy in the form of light, which you can see, and also in the form of heat. Can you feel the heat? You're too far from it, but you know it from experience. All right, so let's try to find out what's in this balloon. We take the flame and we put it there. What happened? The balloon popped, right? And so that balloon had in it the gas helium. Helium does not burn. It does not combine with oxygen. What I'm going to do next is what we always do in science. I'm going to repeat the experiment. So I bring this green balloon down, and did the same thing happen as before? Exactly the same thing? Well, no, the flame went out this time. The first time the flame did not go out. You really have to be very observant about what is happening so you can really enjoy the observations and try to make sense out of these observations and try to have some fun. So now we go to the next balloon. What color is it? Yellow. So we bring this down and we put the flame in. Did that balloon have helium in it? No. That balloon had in it a gas lighter than air. We call it hydrogen. And hydrogen combines with oxygen from the air to form something we call hydrogen oxide. You know what the more common name of hydrogen oxide is? Water, yes, water. So we form some water vapor. And what do we always do in science? So we're going to repeat the experiment with this next balloon, but we're going to do it in the dark. So with the lights down, please. All the way down, all the way, all the way, all the way, all the way, darkness. And I bring you. Ready for this? Here we go. Did you see the ball of fire? Did you see the ball of fire better with the lights on or with the lights off? That's something we have to remember when we do experiments that release energy in the form of light. We do them indoors. We do them in the darkness so we can make better observations. What I'd like to ask you to do now is to look at the same explosion we just had, but we're going to look at it in slow motion. You won't hear any sound. You'll just see the flame going to the balloon, and very quickly, there's that ball of fire again. That was hydrogen gas combining with oxygen that's in the air. Air is a mixture of nitrogen and oxygen. And we're going to do a lot of experiments today with both gases and other chemicals that are formed with these two gases. Now you notice that when we moved from the helium-filled balloons to the hydrogen-filled balloons, that the amount of sound energy increased. So what I'd like to do now, before I begin the next experiment, is to ask you to protect your ears from potential damage by taking both fingers and sticking them in your ears very tightly. I can't do that and do the experiment at the same time, so I'm going to use some earplugs. So I have some earplugs that I will put in my ears very quickly right now, and I really want you to protect your ears. If you can hear the sound of my voice, that means you don't have your ears well protected. Now, I can't hear you, but I can see some of you smiling. That means you heard what I just said. So please protect your ears as we now go to the next set of balloons, and we bring the balloon down. That balloon had in it a mixture of hydrogen and oxygen. A lot more oxygen was available for the hydrogen to combine with to form water vapor in a very uncontrolled combustion reaction. You know what we call uncontrolled combustion reactions? Explosions. That's what an explosion is. And what do we always do in science? So let's repeat this experiment. You protect your ears now very, very well as we do the next experiment in the dark. So here we go. You ready for this? I'd like to ask you right now to look at the very last explosion in slow motion. Once again, you won't hear any sound, but you see the flame coming to the balloon, and there, very, very fast reaction, a lot faster than the combustion or the burning of hydrogen with oxygen that's in the air. Here is the combustion of the gas we call natural gas in this burner. This is an example of a controlled combustion reaction. We see the light energy, and you're too far to feel the heat energy. Such burning reactions, such combustion reactions, we call them exothermic reactions. There are a whole variety of substances that burn. Here's a piece of steel wool that's mostly iron. You know what happens when iron combines with oxygen. What do you get? Rust. Rust is iron oxide. So I'm going to now accelerate the combination of oxygen with iron by putting it in the flame. And there you see that we are forming rust. In this flask, I have oxygen. So I'm going to take this burning iron, I'm going to put it inside, and there you see it. Can we turn the lights down? Turn the lights down, please. There you see, again, the combination of oxygen with iron. Isn't that a spectacular reaction? Would the lights back up, please? This is an example of a reaction, again, that involves the combination of a chemical with oxygen to form an oxide. Now I want to do another experiment, and to do this experiment I have to get a bucket out of here. Actually, it's a big dish pan, and it is empty except for air. It doesn't have anything in it. And to do this experiment, I need some hot water. So can someone please bring me some hot water? Would you please do that? Oh, yes. Hey. Hello, Bucky. Just put it there, Bucky. Thank you very much, Bucky. Thank you, Bucky. Welcome to my lab, Bucky. I'm so glad to see you. I want everyone to notice that Bucky has goggles on. Yes. And of course, I want you to notice that Bucky has a button on here. It says what? Science is indeed fun. Now, Bucky, thank you for coming and helping us with this experiment. Let's see. Let's do the experiment that I was trying to work on here. So, you like that? Bucky is very observant. I want to tell you, Bucky is a very good student. I've had Bucky in my classes here, and he's done very, very well. All right, Bucky, I'm going to take this hot boiling water you brought me. I'm going to put it into the dish pan over here. What do you see coming off the top? Steam. Steam is invisible. You can't see. It's not water vapor either, because water vapor is invisible. This room is full of water vapor. Otherwise, my throat would be drier than it is right now. What do you see coming off the top here? Condensed water vapor. All right, Bucky, what I'd like you to do is take that bucket here of dry ice, and I would like you to dump it right in there. Come right over here. Ready? Here we go. Do it. All right. We're still here. This is how they make fog in the movies sometimes. They take hot boiling water and add to it dry ice, and then you have a fan on it, and you can blow it in any direction that you want. So that was a very neat experiment, Bucky. Thank you for helping with that. Now, Bucky, I know you are a very good student, and you are going to graduate on time, aren't you, Bucky? How many years is it going to take you to graduate, Bucky? How many is that? 1, 2, 3, 4. Bucky's going to graduate. Wait a minute. Wait a minute. Lift up, lift up. Let me see. Lift up again. He's got 4, and I have... Well, we are different, right? Bucky's going to graduate in time in 4 years. I know, Bucky, that final exams are coming up right now, and you probably have to go and study. Is that right? All right, so I would like to wish you the best in your academic pursuits, and I want you also to do well on your final exam. So thank you for coming, Bucky. Really appreciate it. Thank you very much, Bucky. Thanks. Well, the experiment that I'm going to do next is with nitrogen dioxide and other oxides of nitrogen that are in these 3 sealed flasks. Why do you suppose I have these flasks sealed? Because they have in them a deadly poisonous gas, nitrogen dioxide. You can see the color of it. And what I would like to show you is the effect of temperature, of changing the temperature on the color of the nitrogen dioxide. So I have an ice bath right here. I'm going to put 1 flask in the ice bath, leave this one in the middle at room temperature as a reference for comparison purposes, and then this one I'm going to put in this hot bath that I have over here, right? So here we go, and what we will be looking for is a change in the intensity of the brown color. This is our reference point right here. This one is our reference point at room temperature, and then if I take the one in the hot bath, you see that the color is quite a bit darker. That means it has in it more nitrogen dioxide. And the one in the cold bath is a bit lighter. That means it has in it less nitrogen dioxide. Actually, what happens in this mixture of oxides of nitrogen is that nitrogen dioxide, NO2, combines with itself to form something else called dinitrogen tetroxide, N2O4. And that's colorless. And that's what's happening actually in this flask that I cooled off and in the flask that I also warmed up. So more of the colorless dinitrogen tetroxide was formed here. More of the colored nitrogen dioxide was formed over there. Well, we have some liquid nitrogen, and what I'd like to do is use this porcelain dish that's empty except for air. And I'm going to take some liquid nitrogen and put the liquid nitrogen in there. And you see it dances around a little bit until it evaporates because it's cooling down the hot surface that it is in contact with. I'm going to take this flask that has in it the nitrogen dioxide and other oxides, and I'm going to cool it down even more so than I did in the ice bath. I'm going to cool it down with the liquid nitrogen. Let's see, I have a little bit more of liquid nitrogen over here. You can begin to see that you can see that the color is beginning to change, right? Can you see that? It's getting less and less. I put some liquid nitrogen on the side, like so. More is better, right? Well, sometimes. Eh? Not every time. So I will now, you can clearly see that the coloration is less intense in this sealed flask than it is in the other two flasks, right? So I'm going to lift it up, and I'm going to try to show you what is happening over here. You see this blue color? That's a very, thank you. Thank you. This blue color is for another oxide of nitrogen. It's called dinitrogen trioxide. Don't get confused with all of these names. You know, all of these names are important to learn about if you study science, because we need to know what to call these substances so we understand their properties. So the blue solid is dinitrogen trioxide. The brown substance is nitrogen dioxide. And so when this warms up to room temperature, what color are we going to see? We're going to see the brown color again. Another experiment that I want to do, and this experiment I want to do at this end of the table. I'm going to reach down here and get a big can. This can has an opening. Can you see the opening? And it's empty, except for... All right. What I'm going to do is put some water in this can, a clear and colorless liquid, water. I'm going to put it in there. And then the next thing I'm going to do is light the burner, because I want to boil off the water that I just put in the can. So I'm going to turn the gas jet on. And I want a full blast of gas. Then what I'm going to do is take this can, put it on the tripod. Well, let me put this down here first. And heat it. And you know what happens when you heat water. What happens? It boils, it changes into water vapor. And when the water vapor comes out of the opening that we have up here, it's going to hit the cold air, and it's going to condense. So we're going to get condensed water vapor. In other words, we're going to get some fog coming out of here. And I would like you to help by letting me know when you see some fog coming out of here. Because in my lab, we do lots of experiments, and there are lots of good people that help out with these experiments. And you really never know who you might expect to find in my laboratory at any particular time of the year. It's very important for us to...
Ho, 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 ho! Merry Christmas, everybody! Ho, 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 ho! Merry Christmas, everybody! Ho, ho, ho! Merry Christmas, everyone! Ho, 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 ho! Merry Christmas, people! Ho, ho, ho!
Hello,
Merry
Santa.
Christmas!
And welcome to my lab.
Hello, but Sam, it's been a long time. Nice to see you again.
It's been about a year now.
Yes.
I'm happy to see you, Santa.
Oh, yes.
This is a busy time of the year for you. How is Mrs. Claus?
Everyone is doing fine at the North Pole.
And the elves? And the elves?
We're busy making toys for all these lovely kids now.
Now, Santa, did you get the list that I sent you?
Yes, yes, yes. We got the very long list you sent us.
A long list?
Long list here. Mrs. Claus gave it to me personally. Let's see what you got.
Did I get any of the things that were on my list?
Oh, we got some fog here. Yes, here's the book you ordered, Sam.
Oh, you know what they're saying to me?
What are they saying,
They're
Sam?
telling me about the fog.
Oh, so we have an experiment going, I see.
We have an experiment going. It's still going on. And can I get my presents from Santa Claus first?
We do the
Yes?
presents?
Or you want to do the experiment first? Experiment first? Or presents first? Well, let me ask you this. Have I been good? Yeah. Well, then let me get my presents first.
All right.
All right? This is a wonderful book. It's called Galileo's Daughter. It's by a very famous writer. Her name is Deva Sobel, and it is an historical memoir of science, faith, and love. Thank you very much, Santa, for bringing me this.
You're
By the
welcome.
way, did you notice what I have right here? This is, what is this called? Galileo's thermometer. So that's a very nice connection that you made for me, Santa, with this. So, all right, what else? Did I get anything else? Oh, yes.
We have a couple racquetballs for you.
2 rocket balls, yes, they're bouncy balls. We all know that. All right, we'll put them to some good use. Maybe.
And here's your new hat you ordered.
Oh, it's my new cap. Oh, yeah, I like that. What does it say?
Science is fun.
Oh, you can say that louder. Do you believe that science is fun?
Yes.
Oh, thank you very much.
We have
Oh,
a new coffee mug for you.
my own science is fun mug, no less. Look at that.
Yes.
Thank you very much.
You're
Thank you,
welcome.
Santa. Thank you, thank you, thank you. Anything else?
And then the elves sent you a little present.
Oh, the elves sent me an elf. Look at that. Isn't that something? Isn't that something? And look what it says back here. Arsenic. This little container has arsenic in it. You know, this is the 33rd annual Christmas lecture that I give. And element number 33 in the periodic table is arsenic. That's very thoughtful of you, Santa, and for your
you're
elves.
welcome, Sam.
All right, Santa, now, let me show you this experiment, all right?
Okay, I will
so
step
to
back
do
out of
this
the way here for a
experiment,
minute.
oh, you're doing fine.
Okay,
you're
then.
doing fine. Just give me a little room here, and let me put my gloves on, because I want to pick up that can that is hot. This can is very hot right now, and I'm going to pick it up and take this rubber stopper. Before I pick it up, I'm going to stopper the opening so you don't see any fog coming out anymore, like this. And then I have a tray here with some ordinary ice. What I'm going to do is put the can in the ice just like this to cool it off. Cool it off. What's happening to the can?
Oh.
Look what's happening to the can.
Very good.
You like that, Santa?
Very good, Sam. Good job.
Thank you, Santa. Now what we want to know is what made the can collapse. The can is getting crushed,
Oh.
right? I think everyone who has been watching the experiments can try to think about the explanation for this. What did I do here? I was boiling some water when we had a very nice surprise and a visit, right? And the water was coming out of the opening, right? Be quiet over there. Actually, it can't be quiet. It's got to do its natural thing. And the water vapor was coming out of the opening. It was sweeping along with it some air. So there was less air inside the can than there is outside the can. And so the pressure inside got to be less than the pressure outside. And this huge, strong, invisible giant we call the atmosphere crushed the can. So that's how this experiment works. Did you like that, Santa?
Oh, it was beautiful, Sam.
Thank you very much for coming by.
You betcha.
Please have a very Merry Christmas.
You too,
Merry
Sam.
Christmas. Thank you very
You
much.
betcha.
Santa.
Everyone have
Thank
a
you.
Merry Christmas.
Thank you.
Ho, 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 ho. Merry Christmas, everybody. Merry Christmas. Ho, ho. Merry Christmas.
The next thing I'm going to do is to take a very bouncy rubber ball. You see that? And I'm going to put this rubber ball in this thermos bottle. We call it a Dewar flask. It's insulated. I'm going to put the rubber ball in there, and you see what happens to the liquid when a warm object, a hot object hits it. The liquid starts to boil, right? So I'm going to put some more. Oh, I'm running out. So I got some more over here. I put some more in there. How's my aim? Good? All right, so we're cooling down the rubber ball. And let's see, I need to push the rubber ball down a little bit here. Make sure it's really cold. And what happens when I put the tongs in there, the metallic tongs in there? More boiling, right? Because the tongs are warmer, right? And I can tell you right now, actually, you can guess what I feel in my right hand right now. Feels cold, right? Because the metal is a good conductor of heat, right? And we all know that heat flows from a warm body to a cold body, right? So that's what I'm going to do now is make sure this is really cold. And then I'm going to put my glove on and come out to the front. Take this flask that has the ball in it. I got to get the ball out of there, so I can't do that very easily. I'm just going to put it into this mug right here to see if I can do that. All right, that's in there. Here we go. Cheers. Now I have to get rid of the liquid nitrogen that's in there. So how do I do that? I reach back and get this metallic object like this and pour it out. See, you want to keep the ball in there. Hits the floor. The floor is warmer than the liquid nitrogen, so the liquid nitrogen boils off. All right? So then I'm going to take the ball out now, and I'm going to see what happens when I try to bounce it. What happened? That was a shattering experience. Just trying to be humorous here. I'd like you right now to look at that in slow motion. You won't hear the ball break, but there it is. That's coming pretty soon. And it broke into small pieces because it's no longer rubbery, no longer elastic. And I'd like you not to pick up any of these pieces until they warm up to room temperature, because you'll get a very bad frostbite if you pick it up right now. All right, so let's move on and do another experiment with liquid nitrogen. This experiment we're going to do with taking a gas from this cylinder. This is a tank that has oxygen in it. What I'm going to do is take the oxygen and let it pass through the plastic tubing that I have here into a copper coil that I'm going to cool off with liquid nitrogen. So here's another thermos bottle with liquid nitrogen in it, and you know what's going to happen when the warm copper tubing makes contact with the liquid nitrogen. What's the liquid nitrogen going to do? It's going to boil off, right, like that, just like that, see? I'm going to turn the valve on, and we're looking for a liquid to be coming out of the tube. And you see this tube here that was very flexible. I can let go of it right now. It's frozen. You see that? And what we're going to try to do is to collect the liquid that's coming out. We're going to collect the liquid in this test tube. Can you see a coloration to the liquid down there? What color do you see? That's liquid oxygen. Liquid oxygen is blue. I have to replenish my supply of liquid nitrogen up here. Liquid oxygen is blue, and it's a very concentrated amount of liquid in there. I want to fill up the tube with oxygen as I fill up the Dewar flasks here with nitrogen. And then I'm going to put my glove back on. My glove is way over there, so I'm going to stop this and turn this off, take this out, You notice I'm very careful not to touch anything very cold because I will get a very bad frostbite if I do that. And we don't want that to happen, neither to me nor to anyone else, right? Right. So the next experiment I'm going to do is with this very strong magnet. This is called a horn gap magnet. And what I want to show you is how strong this magnet is by taking my pocket knife and putting it between the poles of this magnet. So there it is. See? It's a very strong magnet. Try to pull it out. Try to pull it out. OK, it comes out. It really comes out. So you can believe that this is a strong magnet, right? You don't believe it. You can see that it is a strong magnet, right? So what I'm going to do is take some liquid nitrogen and put the liquid nitrogen between the poles of the magnet. Just pour it in. What's happening to the liquid? Just passing through, right? So the liquid nitrogen does not have any magnetic properties. The next thing that I'm going to do is take some liquid oxygen that I have in this tube right here, and I'm going to pour the liquid oxygen and see what happens. Whoa. And you see the liquid held between the poles of the magnet, right? The liquid is held between the poles of the magnet until it evaporates. This tells us that liquid oxygen has magnetic properties. We call that paramagnetism. Paramagnetic is the property of not only liquid oxygen, but gaseous oxygen. So what I want to do with the remainder of the oxygen, by the way, this is a very highly concentrated amount of oxygen, a lot more than what's in the air because it's condensed. So I want to do an experiment with this. And to do this experiment, I need to get another prop from over here. Actually, this is the only prop I'm going to use because all the other things that I use are real equipment and chemicals that we use here. So what this is a cigarette. I'm going to light a cigarette. Don't do it, he says. I'm just going to light it, okay? You're right. Bad stuff. People actually like this. Here's what I'm going to do. I'm going to take this cigarette, put it in this beaker. It's a lit cigarette, and then I'm going to take the oxygen from the tube. And I want you to see this very clearly. Here's the oxygen, and that's what I think you should do with all cigarettes. To do the next set of experiments, I would like you at this time to welcome my longtime colleague and friend, Dr. Rodney Schreiner. Rod?
Hello.
Hello, Rod.
Hello, Bassam.
What do you have for us today?
Well, you know that molecular oxygen is paramagnetic, right?
Yes, it is paramagnetic.
Means it's attracted to a magnet.
Yes.
Are any other gases in the air?
Well, nitrogen is not.
Okay.
Carbon dioxide
Carbon
is not.
dioxide is not.
Water vapor is not.
Water vapor is not.
Argon is not.
Okay. So that means that only oxygen is attracted to a magnet. You know, we can use that fact to determine how much oxygen is in a gas.
All right.
And I have a device that will do that for us right here. This is actually a medical instrument which is used in hospitals. And it has a tube which draws air into it, into the instrument, and the instrument displays on the screen the percent oxygen in the gas that's being drawn in. Currently, it's reading 21% oxygen. So that's what we expect because it's drawing air into it. It also makes a graph of how much oxygen there is, starting at 0, going up to 100, and we see a line down here at 20%. Now, this is used to monitor the breath of a patient. So not only does it measure how much oxygen is in the air around us, it also can measure how much oxygen is in the air when you exhale. So I need a patient. Would you be my patient?
Of course.
What you need to do is take the tube and hold it in your hand and then breathe into your hand.
Just breathe normally?
Just breathe normally into your hand.
Is this going to hurt?
No, it should not hurt.
Just breathe.
Just breathe. Okay, so as Bassam is breathing, the machine is drawing the air that he exhales into it, and it is making a graph. And we can see on the graph that there are dips. When it goes down means that he's exhaling. And the machine also shows us at the top here that the air that he is exhaling is 16% oxygen rather than the 21% that's in the air around us. So when we inhale, we take in oxygen in the air, and some of it is absorbed. So when we exhale, there's less oxygen, and only 16% or so in Bassam's
This
breath.
works because oxygen is paramagnetic?
Because oxygen is paramagnetic. The machine is detecting the magnetism of the oxygen in the gas that flows through it. Now, it does go all the way up to 100%, and sometimes patients in hospitals are given extra oxygen in order to help them breathe. And I want to show you that it does rise if there's more oxygen. So I'm going to generate some oxygen in this flask using an ordinary liquid that many of us have around the home. It's hydrogen peroxide, the disinfectant or antibiotic that you can buy in the pharmacy. And if you've ever used this as a disinfectant on your skin, you'll know that when you put it on your skin, it starts to bubble. And I'm going to increase the bubbling of this by adding to it some manganese dioxide, just a little bit. And the flask begins to bubble vigorously. The bubbles that are produced by hydrogen peroxide are oxygen. So when I dip the intake tube into the flask, the machine will begin to register that there is more oxygen. And let's see. Yes, the graph is beginning to go up. I think we can see the graph going up, and the number is going up as well. We're up to 29, 30-some%. So as the hydrogen peroxide decomposes and produces oxygen gas, the registration increases up to 40% now. And if I take it out, then it will again draw ordinary air, and the graph will go down, and so will the reading. So it's detecting oxygen because oxygen is magnetic. That's how it differentiates between oxygen and the other gases that are coming into the tube.
Well, that's very interesting, Rod. Is there, yes.
Thank you. Thank you.
Now, is there a way to detect how much oxygen is in the body?
Well, there is another medical instrument which will help us do that, and that's called a blood oximeter. It measures the amount of oxygen that's in your blood as it circulates through your body. And it has, first I need to turn it on. There we are. It's on now. And it has a probe that you connect to your finger.
Any finger?
Any finger.
How about this one?
That one? Okay,
All right.
We'll put it on
Okay.
there. And in a few seconds, it begins to register the percent saturation. That is, how much of the maximum amount of oxygen does Bassam have in his blood? And it's currently reading 97%. So,
Is that good?
that's very good. That's very good.
It doesn't even hurt.
I hope not. I hope not.
But Rodney, how does it work?
How does it work? Well, if we look inside this clip, there is a little red light. And that little red light shines through your finger. And why is that important? Well, because when your blood absorbs oxygen, it changes color. Your blood is what color when it has no oxygen in it? It's blue, that's right. And you can tell that it is blue if you look at the veins in your arms. They are blue. That's the blood which is going back to your lungs. It's blue like the liquid in this flask. And when your blood goes through your lungs, it encounters oxygen just like the liquid in this flask will encounter oxygen if I give it a little shake. And it turns red. So when the blood gets oxygen, it turns red. Now, why is that important? This is your blood when it has oxygen. This is your blood when it doesn't have oxygen. Red with oxygen, blue without. And now this little medical device has a red light in it. That red light can shine through your finger. It can shine through your finger when it's red, meaning lots of oxygen. But if you don't have much oxygen, the red light doesn't come through. So what this machine is doing is really measuring how red you are. And the redder, the better. Thank you. Thank you.
Thank you very much, Rod. Thank you very much. Thank you. Very fascinating how we now have a lot of advances in technology that enable us to make measurements, painless measurements of the type that we just saw here. Well, to help with the next set of experiments, I'd like you at this time to welcome Elizabeth. Elizabeth? Hi, Elizabeth.
Hello.
How are you?
I'm doing well, thank you.
Do you have your goggles?
Just 1 second.
All right.
Thank you. All right. Now I'm prepared.
Now, of course. What are you going to show us?
Well, today I'd like to show you some reactions involving hydrogen peroxide.
I know hydrogen peroxide. That's what you can get in a drugstore. It's used as an antiseptic.
Right. And have you noticed that when it touches your skin, it bubbles?
Yes, it does give off bubbles when it touches the skin. What kind of bubbles are those?
They're oxygen bubbles. When hydrogen peroxide touches certain things, including skin, it decomposes into oxygen and water.
Very interesting. Does it do the same thing with other items, other materials other than skin?
Yes, it also does it with manganese dioxide.
That's what you have there.
Right. I have it prepared in little packets so it's easier to handle.
And do you have any hydrogen peroxide?
Yes, I have some in these 2 bottles.
So the clear and colorless liquid at the bottom of those 2 plastic bottles is hydrogen peroxide. Is that the same hydrogen peroxide we get in the drugstore?
No, it's not the same. The hydrogen peroxide you get at the drugstore is a 3% solution. This here is a 30% solution.
Oh, so this is a lot more concentrated
Right.
then. All right. Shall we do the experiment?
Okay, we're going to drop these little packets of manganese dioxide into the hydrogen peroxide and see what happens.
Whoa. So the oxygen bubbles that are coming out, by the way, is it okay if I touch this?
No,
No?
it should be very hot.
Should be very, how about if I try to touch it very gently? It is very hot. So this reaction releases a lot of heat and causes the water from the hydrogen peroxide to boil off, and when it hits the cold air, it forms fog, and that's what we saw there.
Right.
Can we see that again?
Sure.
Very nice. That's very nice. And I'm sure people notice that the size of the bottle has become smaller. The bottles have shrunk. These are plastic bottles. Have you heard of something called shrink wrapping? How does that work? You take a piece of plastic and what do you do to it? You heat it, and that's what happened in this reaction here too. Is there a way, Elizabeth, to slow down the oxygen bubbles?
Yes, we could add some soap. Here I've already prepared a mixture of soap and manganese dioxide.
That's what is at the bottom down there.
Right.
All right.
And I have another 30% solution of hydrogen peroxide, and we'll add that and see what happens.
I can see soap bubbles all right. A lot of soap bubbles. Wait a minute, this is getting out of control maybe. Oh, wait a minute. That's really cool, Elizabeth.
Yeah. I have one more cool experiment that I'd like to show you.
All right.
Here I have another solution of hydrogen peroxide, and this solution is called copper sulfate. And I'm going to mix them together in this funnel and see what happens. I'd like to do this in the dark, please.
That's really cool, Elizabeth. That was hydrogen peroxide and some copper sulfate and a couple of other dyes in there, right? And this is called chemiluminescence. This is the release of energy in the form of light, but not in the form of heat. That was a really neat experiment. Elizabeth, thank you very much.
Thank you.
Thank you. Now I ask you to focus your attention on this part of the lecture table where I have a glass beaker. This beaker is empty except for air. I want everybody to look at this beaker. This beaker has a volume of 2 liters. If you look at this beaker, you just learned how big 2 liters is, and you cannot unlearn it. You may forget it. That's different. I'm going to take a magnet that's coated with Teflon and put it inside this beaker. It's sitting on a magnetic stirring motor. I'm going to turn the light on so we can see it a little bit better, and then turn the switch so that you can see the magnet spin. Can you see it spin? I'm going to mix 3 clear and colorless liquids out of these flasks into this beaker. We'll see what happens. Here's the first one. Anything exciting happening now as I add the second one? Tornado is kind of exciting. Yeah, you can see that. Let's make a bigger tornado, just like that, right? And a volume increase. That's not terribly exciting. We know about that. I add the third liquid, and well, I don't see anything happening. How come I don't see anything happening? I'm not looking. What's the big deal about looking? The last time I looked, the color of the liquid in the beaker was blue. You tell me when to look. Shall I look right now? No, no. You tell me when to look. Right now. I don't want to trip over anything. Tell me when to look. Right this second? Yes? Yes or no? Make up your mind. Right now. You sure? I don't want to trip over anything right now. You tell me when to look. Should I look right now? It's blue. Every time I look at it, it's blue. All right. What is it that you are doing that I was not doing? You are looking all the time, right? So when I asked you, when should I look, what should you have said? Look all the time. If you don't look all the time, you miss out on a lot of exciting and fascinating changes. This is an example of what we call a chemical oscillating reaction. We have in there a mixture of about 8 or 9 different chemicals, including water, hydrogen peroxide, potassium iodide, manganese sulfate, sulfuric acid, potato starch is in there. And I want you to know that this yellow color that we see right now is the color of iodine, what we call iodine in the vernacular. And when it combines with potato starch, it gives this deep blue color, which is almost black right now. This is a very fascinating system, and this is why we do scientific research, in order to understand how these captivating and fascinating chemical reactions take place. To help with the next experiment, I would like you at this time to welcome a person who has just joined my lab, and that is Mr. Jim Maynard. Jim? Hi, Jim.
Professor, how are you doing today?
You're welcome.
You know, there's nothing better than science, especially in my life, and there's nothing I appreciate more than a good demonstration. So hopefully I have one here for you today.
All right, what do you have for us? We have this long glass tube, and that's filled with what?
Nitric oxide, NO.
Nitric oxide, and then you have something over here.
This is a clear and colorless liquid called carbon disulfide.
What are you going to do?
I'm going to insert this syringe, I'm going to draw some of this out and put it in the big tube.
So this is a sealed tube that has in it the colorless gas nitric oxide, NO. And can I be doing something else at the same time that you're doing that?
Oh, would you mind lighting my torch there for me,
Light
the
this?
propane torch?
Sure, I can
That would
do
be
that.
great. Thank you very much.
All right.
Okay.
So you're going to put the carbon disulfide liquid inside this tube that's filled with nitric oxide.
Yes, I am.
All right. Without letting any of the nitric oxide
Well,
out.
Not too much, anyway.
Well, I can
And
see the liquid dripping down, yes.
Uh-huh.
You're squirting it in.
Oh, and it's all in.
All right, what are you going to do next?
Okay, I'm going to mix this up a little. Now, this is building up quite a bit of pressure because carbon disulfide has a very high vapor pressure. So I'm going to take this down, and now I'm going to mix it up a little.
So you're mixing the gas with the liquid that you just
Right.
added.
And the liquid is becoming a gas and mixing here as I invert it. Okay, that's probably sufficiently mixed for my purposes. Now I'm going to get back up here and set it in and begin the experiment. Some of you might be able to hear the gas escaping. Okay, may I have my blowtorch, please?
All right, there we
and
go.
could we turn down the lights, please?
That was very impressive, Jim.
Thank you.
Let's take a look at that in slow motion. You won't hear any sound, but we will see the flame shooting down and Jim trying to get out of the way there.
Thank you again for
Thank you
having
very
me.
much, Jim. Thank you. Thank you very much. Our next experiment will be done in this large round-bottomed flask, which has a stopper on the top and has a clear and colorless liquid at the bottom. You know, in chemistry, we like to mix things together and see what happens. So I have a cylinder that has in it a clear and colorless liquid. I'm going to add it to the flask and then put the stopper back on. And we see that there's a color change already that tells us that the chemical reaction is taking place. But we have to mix the chemicals together very intimately and work at it a little bit. And you begin to see some more changes. In fact, I begin to see myself. Can you see yourselves in this? Oh. What we have done here is deposit a very thin film silver on the inside of this glass flask. We made a mirror. And during the holiday season, this is an appropriate experiment to do because we want big holiday ornaments. And what I'd like to show you is even a bigger one that we made before. So when you drive around town during the holiday season and you see large silver ornaments like this, you know where they were made. I want to thank you for coming to this very special presentation. You have been just a wonderful audience, and I wish you the best in everything that you do in life. And remember, no matter what you do, that science is fun. Thank you very much, everybody. Thank you. Thank you. Thank you very much. Thank you.
To order a copy of this program, please send a check or money order for $30 to 2002 UW Christmas Lecture, Department of Chemistry, University of Wisconsin, Madison, Wisconsin 53706. Please do not send cash. Credit card and COD orders cannot be accepted.